Alright, so this is we're going to start looking at what happens when we pull loops of wire through magnetic fields and look at what happens to the energy and the forces that result from this motion. So we have a loop of wire that's pulled through a magnetic field. As it both enters and leaves a magnetic field, the magnetic flux through the wire changes. Well, that induces a current on the wire, and that induced current experiences a force due to the magnetic field that it's passing through. And so as you're pulling this wire, you have to be applying work in order to pull this wire through the magnetic field. Ultimately, that energy that you apply to the system gets transferred into thermal energy in the wire. The wire should heat up during this process. So let's look at how this works. So if we go back to problem O2, we see that a loop of wire being pulled out of a magnetic field like this, that the EMF, or the electromotive force, should be B times L times V when we actually work out the change in flux over change in time. Now the direction of the current should be going this direction. This is a magnetic field going into the page, so it should induce a current in the direction to put more magnetic flux into the page. And so we can actually calculate the current in the wire by dividing by the resistance of the wire, R. Now there are three segments of the wire that experience force: the bottom segment, the left-hand segment, and the top segment. It's worth pointing out that both the bottom segment and the top segment have the same magnitude, they're just in opposite direction. That's because the magnetic force will be magnetic field strength times current times length of the wire within the magnetic field, and for these, all three of those values are the same. So the only one that experiences any magnetic field at all that's interesting is this side over here, or any magnetic force that's interesting is the left-hand side. And the way I would calculate that is I times B times L. And I can plug in what I is I is B L V over R. So we get the force that is being applied on the wire due to the magnetic field is B squared L squared V over R. Which means if you're pulling this wire through this magnetic field at a constant speed, that is also the force you would have to apply on the wire. Now, if we calculate the power, or the amount of energy that's being used up, power, remember, is the rate at which energy is being used up. Force times velocity is one way to calculate the power, especially if your force is constant and your velocity is constant. And another way to do it is to do I squared over R. And what you find is you get the same amount of power. So remember, this would be amount of energy being used up per unit of time. If you knew the amount of time it took for this to occur, you could actually figure out the amount of energy that you needed to apply to the wire. So basically what you need to know is how long you pulled the wire out of the magnetic field. So let's look at this problem here. Let's say we have 4 loops of wire shown above, and they're all going to be pulled at a constant speed through this constant magnetic field. And edge lengths are either L or 2L as shown in the drawing. So A would be L by L, so B would be L by 2L, C 2L by 2L, and D 2L by L. We want to rank the 4 terms or loops in terms of greatest EMF to least EMF as it gets pulled through the magnetic field. And think of it both entering and exiting the magnetic field. The answer is that C and D should have the greatest. The main reason is that this length here is the only length that matters, and they both have this length 2L, and these both have the length L. Remember that this direction is changing by your velocity V. Let's look at this problem here. We have a problem where we have 20 turns of rectangular coil wire, and it has an area of 0.25 meters by 0.15 meters and a resistance of 5 ohms. And it says in position 1, shown to the left, the loop is entirely within a uniform magnetic field with a magnitude of 0.2 teslas. The field is directed out of the page and perpendicular to the page. The loop is then pulled to the right at a constant velocity until it reaches position 2, which is just outside the magnetic field in 0.5 seconds. What we want to do is calculate the following things: the average induced EMF in the coil, the induced current and its direction, the power dissipated in the coil, and the average force needed to remove the coil from the magnetic field. So let's first of all find the average EMF in the coil. Remember, B times L times V would be the EMF, and I multiply by N the number of loops. So the way to find V is it looks like it's going to move 0.25 meters at 0.5 seconds. and we plug everything in, we get 0.3 volts as the average induced EMF. Now, average induced current, I would do average induced EMF divided by resistance, and so I get 0.06 amps as the average induced current. Now, for its direction, we had a magnetic field that's out of the page, decreasing that flux. Its direction should be counterclockwise by the right-hand rule. Now, the average power dissipated in the coil, P equals I times V. Well, we know I and we know V, so you can actually just calculate it out. 0.06 times 0.3 gives you 0.018 watts. And finally, the average magnetic force that we need. And I did N times I times B times L, where N is, well, the number of loops, because this current is in each of the loops. And so we get the average magnetic force is the average force is 0.036 newtons in order to pull this loop of wire out of the magnetic field. Now, it's worth pointing out I found this problem in either a review set for an AP exam or a former AP exam. Don't remember exactly what it was, but this problem has shown up, or problems similar to it have shown up on AP exams in the past. Now, the other thing to point out is that changing the magnetic flux, if it induces an EMF or a voltage, it must also be inducing an electric field because, well, remember that if you take electric field dot ds or electric field and integrate it based on distance, you get voltage. What this means is that this value, electric field dot ds, is actually equal to negative the magnetic flux. What this means is a changing magnetic field induces an electric field. That's actually a pretty cool idea when you think of it. The changes in magnetic field induces an electric field. What we'll see later on is that a change in electric field can also induce a magnetic field. This works in both directions. So that kind of wraps up our lesson on energy and induction and really force and induction and how these things kind of work in, well, concert with one another.